Good evening to all. I'm going to present the effect of hydrogen on tensile behavior of different lower steels, which has a different dynamic strength behavior and in the polars of Walsh instrument. So basically, I was to emphasize that there are vast research on the hydrogen embrittlement of different steels and different materials, but all these are mainly concerned on the room temperature and less than 150 degrees Celsius. Because of it is believed that the hydrogen effects are disappeared after above 200 degrees Celsius. That is why there are very less research on the hydrogen embrittlement in the dynamic static behavior of nuclear reactor preservable steels. So this is the outline of presentation. I will just give introduction about the structural integrity of reactor preservable steels and experimental methods and resultant discussions followed by summary. So coming to the introduction, for any component at high temperature or whatever in any applications, the structural integrity of a component is very important regarding the safe operation of the component, particularly in the reactor, in the nuclear field, the reactor pressure vessels, which has a very complex environment of irradiation and high temperature water chemistry and with hydrogen and high temperatures around 280 to 300 degrees Celsius, and also some additional stresses. This gives the material prone to different damages during the in-service conditions. And there are different. These are the different damages which usually occur in the nuclear reactor operation. So basically, there may be a possibility of thermal aging and DSA and irradiation embrittlement and fatigue, also the corrosion of the reactor pressure vessel taking place. And one more thing is that because of the reactor pressure vessel steels are exposed to the water coolant, so it may also undergoes to environmental assisted cracking like stress corrosion cracking and stress corrosion corrosion fatigue, etc. And also some boric acid corrosion and also fluoride assisted cracking. And one more thing is hydrogen embrittlement. All these gives the loss of fracture toughness and tearing resistance reduces the reactor pressure vessel steels, which also reduces the resistance to unstable brittle cracking, which shifts the DBDT curve in the high temperature regime. So all these things makes the reactor pressure vessel steels to brittle fracture. So here I'm showing how the hydrogen picked up in the reactor pressure vessel steels during the operation of the reactor. So this is the cross section of the reactor pressure vessel steel with consisting of reactor coolant with additional intentionally added hydrogen, and this is the cladding and heat affected zone, and this is the reactor main pressure vessel steel, which is made up of lower steels. So because of this welding of cladding material of stainless steels, there is a possibility of it gives the more inhomogeneous structure in the clad material, and also it is less resistant to the environmental assisted cracking. And because of that, there is a formation of cracks inside the cladding, and also the internal cracks inside the clad materials. This figure shows the in the nuclear application, in the reactor applications, there are formation of the failure of the crack, failure of the clad material inside of the reactor pressure vessel. So all of these and these formation of these cracks, which causes the interaction between the water coolant and the structural component of stainless steel, and which makes the corrosion reaction of which gives the development of produces the hydrogen at the crack tips, and also interacts with the brittle phases like manganese sulfide in the steels, which ultimately causes the evolution of hydrogen, which directly goes into the reactor pressure vessel, and which is very important to conserve evaluate the hydrogen embeddment of the reactor pressure steels. So basically there are different parameters which affects the hydrogen embeddment of any component. So on the mechanical part, mainly the stress intensity factor and the strain rate, the strength of the material and the type of loading which affects the hydrogen embeddment. On the other hand, the environment, which has the source of the type of source and the concentration of hydrogen, which affect the hydrogen embeddment of material, and also the temperature and pH of the high temperature water coolant. On the material point of view, there are the microstructure and the grain size and composition of the steels, which largely affects the high embeddment effect of the component. These are the few characteristics of the hydrogen in low alloy steels, which are it has a low solubility, but it has a high diffusivity compared to the austenitic stainless steels, and which has and also it has a large molar partial volume, that is induces the hydrostatic stress fields inside the material, and also it has the large electronic interaction, which creates the dislocation motion, and the interaction enhances the hydrogen inside the low alloy steels, and also promotes the low strain localization in the material. So we have selected the two different materials, which have one material which is similar to 508 class 3, which has a high susceptibility to DSA, and another is nickel molybdenum bromaloy, which is similar to 508 class 2, which has a low susceptibility to DSA. And the materials are heat treated with homogenizing and temperature conditions, which has a grain size of almost equal on the both materials. And this table shows the chemical composition of the light, and from this the presence of amount of free nitrogen in the material, in the steels, we can broadly say that the effect of DSA in these materials, which has the 29 manganese molybdenum nickel steels has 10 times more free nitrogen inside the material. So to evaluate the hydrogen effects in these two steels, we use the electrochemical method of charging, hydrogen charging of the steels. So basically we use the platinum counter electrodes and the sample as a working electrode, and we applied a current density of 10 milliampere per centimeter square for 7 hours. And all this charging was carried out in the galvanized static mode with the electrolyte of sulfuric acid with arsenic oxide. And after the hydrogen charging of 7 hours, we coated with copper with this electrolyte with 5 volts and then to 8 to 10 minutes. And this is the schematic of the sample we used, and also we found the hydrogen content of the inside the material after hydrogen charging of 7 hours at this current density, which was found to be around 5.5 ppm. So coming to the results, this is here I'm showing the dynamic behavior of this 20 manganese molybdenum nickel stainless steel. We evaluated the dynamic behavior from room temperature to 500 degrees Celsius at different strain rate from 10 to the minus 5 to 10 to the minus 3. And we can see from here the variation of yield strength and ultimate tensile strength over the temperature range. And we can see there is a strong DSA effect from 250 to around 350 degrees Celsius at the strain rate of 10 to the minus 3. And the strongest effects of DSA were found to shift towards lower temperature when the strain rate is decreased. And here I'm showing this the strain rate sensitivity measurement at different temperatures. And we observed at 250 degrees Celsius and about 250 degrees Celsius we observed negative strain rate sensitivity in the material. We also try to calculate the appearance or disappearance for the actuation and for the surge in this, and found that 1.71 electron volts for the disappearance of fluorescence in this stream. Now coming to the effects of hydrogen on the tensile properties of both these steels, here I'm showing the effects of hydrogen in the 20 manganese molybdenum nickel steel at 250 and 280 degrees Celsius at different strain rates. So here it shows the a variation of ultimate tensile strength with different strain rates. And from this we can see that the tensile strength was decreased after the hydrogen charging. In the both cases, at the both temperatures, 250 and as well as 280 degrees Celsius, at all the strain rates. Similarly, the uniform elongation was also decreased after the hydrogen charging at both temperatures. It's important to mention that the effects of decreasing the tensile strength as well as uniform elongation is more at 280 degrees Celsius compared to the 250 degrees Celsius. And here I'm showing the variation of reduction in area for the different strain rates from 10 to the -4 to 10 to the -1. And we've seen that the strongest effect of dynamic hydrogen effects at 10 to the -3 at 280 degrees Celsius, whereas at the decrease in temperature, the strongest effect was shifted towards higher strain rates, and it was found that at 10 to the -2 there was the strongest effect of hydrogen in the stream. And the drop of at 280 degrees Celsius found that around 90% drop in the reduction in area compared to the at 250 degrees Celsius. Here I'm showing the effect of hydrogen in the steel 22 nickel molybdenum chromoly steel, which has a less susceptibility to DSA at 280 degrees Celsius. And you can see that the tensile strength, where there is a minimal change of tensile strength after hydrogen charging, whereas at the reduction area where there is a significant drop of reduction area after hydrogen charging at 10 watts, particularly at 10 to the -2. Now, comparison between these two steels, you can see that the hydrogen effects are more in case of 20 manganese molybdenum nickel steel, which has high susceptibility to DSA. It has more or less, it's almost 90% drop in the reduction area. And from this we can say that there is a stronger effect of hydrogen in the higher susceptibility to DSA steels. And we try to analyze the fracturography of the samples. And in the case of 20 manganese molybdenum nickel steel, there was a large cracks with large microwides, as well as highly localized shear dimples, which are also, we also see them quasi-cleavage facets along with some intergranular cracking. And this figure shows that 280 degrees Celsius in the higher, stronger DSA material, DSA steel. And similarly, we see in the highly localized shear dimples and also brittle cleavage fractures, and along with this cleavage intergranular cracking. And we also try to see the mode of fracture. We see that without hydrogen there is normal cup and cone fracture, and there is with hydrogen there is a local shear dominant failure of the samples in both steels. So there are different mechanisms proposed for hydrogen abridgment of steels, but we think that at 280 degrees Celsius in these steels, it's not the single contributor mechanism. There is a combination of different mechanisms, like in hydrogen enhanced decohesion embrittlement, which causes the quasi-cleavage brittle fractures and intergranular cracking, and also hydrogen enhanced local plasticity, which gives the dislocations, shielding. Yeah, it's almost finished. And also another mechanism is hydrogen enhanced strain-induced vacancies, which also contributed in microwide formation and reduction ductility of the steels. Finally, summary: the RPV steels, which has the strongest DSA, shown the stronger effect of hydrogen tensile properties. The fracture analysis showed the localized shear dominant failure with facets and intergranular fractures. both DSS as well as RPV steels. Thank you.
Thank you for your contribution, which is in fact in this long story of the effect of hydrogen. Maybe we can have one question. Yes, please.
It was a nice presentation, and you said nothing about the mechanism of hydrogen and dislocation interaction.
But
What do you think about it?
No, just a preliminary study. I have not started studying the TM, not yet. I need to analyze the TM transmission.
When you can't suppose anything.
Because we see from the fracture analysis, we see that there is a localized, these are localized shear dimples. It's not over the sample, so only localized regions, it's not on the whole surface.
Thank you.
So maybe one more important question? No. Thank you very much. Thank you again. And the next contribution will be given by a student of mine on the damage evolution in thermomechanical loading of stainless steel. Mr. Petraš.
Thank you, Mr. Chairman. Good afternoon, ladies and gentlemen. Thank you all very much for coming today. Let me introduce myself. My name is Roman Petraš, and I'm from Institute of Physics of Materials in Czech Republic. And in today's presentation, I'd like to talk about damage evolution in thermomechanical loading of stainless steel. After a short introduction and experimental details, we will look at the result section. First of all, I'd like to talk about the mechanical behavior or mechanical response of material on thermomechanical loading. Then we will continue with the crack initiation and crack propagation, and then I will discuss loading conditions on the fatigue life, and finally there will be some time to draw conclusions. Design and construction of novel, more efficient installations working at elevated temperatures require materials resisting severe loading and environmental conditions. Thermal and mechanical stresses in components during service produce variable strains, and this leads to initiation and propagation of the fatigue cracks. And this phenomenon is known as a thermomechanical fatigue. And in order to prevent premature failure of complex systems and to predict the fatigue life correctly, the investigation of the thermomechanical fatigue behavior as well as damage mechanism is necessary. Material used during investigation was Sanicro 25, which is high alloy austenitic stainless steel. And this material have been developed for using superheaters, reheaters in power plants working at temperatures 700 centigrades. And this new grade shows very good resistance to steam oxidation or corrosion and has higher creep rupture strength than the other austenitic stainless steels available today. And there you can see the composition of the material. After production of crude shape of the specimen, they were annealed at 1200 centigrades for 1 hour, including air. And the gauge line of the specimen was mechanically and electrolytically polished. There you can see the surface of the specimen before cyclic loading. Average grain size was about 25 micrometers. However, grain size up to 200 micrometers were also present in the structure. And grain boundaries are decorated by carbonitrides with typical size of 200 nanometers. In the following slide, you can see some details of specimen geometry as well as mechanical testing conditions. Tests were conducted using standard servo-hydraulic testing machine, and triangular waveform was used for thermal and mechanical straining. Two types of loading were applied to individual specimen, namely in-phase and out-of-phase type of loading in a temperature interval from 200 to 700 centigrades. Moving to the next slide, we can see the mechanical response of material to two types of loading. And there you can see cyclic hardening and softening curves. we can see that cyclic hardening is typical for both types of loading, for in-phase and out-of-phase. And premature failure or fracture prevents reaching saturation region in phase, which results in lower fatigue life. Thermomechanical fatigue leads to or results in initiation of multiple fatigue cracks, and this is due to synergic effect of varying temperature and strains along with the corrosive environment. And in order to investigate the damage mechanism, secondary cracks were observed using scanning electron microscope. And from this figure you can see the surface of the specimen at the end of the fatigue life. The specimen was subjected to in-phase type of loading. And we can see the surface is covered by a thin oxide layer, but it's not homogeneous. And thicker oxide bands can be detected on some grain boundaries, and fatigue cracks are developed practically exclusively at the grain boundaries, as can be also seen in the detail. Damage mechanism evolved differently in case of out-of-phase loading, and we have found that more homogeneous and thicker oxide layer was developed on the surface, and transgranular cracks running on the surface were typical for this type of loading. In order to investigate the development of the crack within the material, focused ion beam cuts were performed. And in this figure you can see the cracking, you can see oxidation and cracking of the grain boundaries. And cracking of the grain boundaries in the early stages of fatigue life leads to early macro crack initiation and its rapid growth in the tensile part of the cycle at increasing temperature. As was mentioned, the different damage evolution was found in out-of-phase loading, and there you can see the crack developed from the oxide layer. But let's have a look at the crack initiation, and we have found that first of all, sufficient thick oxide layer must be formed in the while specimen is in compression at the maximum temperature, and this oxide layer is brittle and becomes cracked in the tensile part of the cycle at the tensile part of the cycle at the lowest temperature. And detailed inspection of these developed cracks in the oxide revealed that the cracks facilitate the access to oxidizing atmosphere locally to the metal surface in the compression at the high temperature, and this leads to formation of V-shaped grooves, as you can see here, and these grooves becomes cracked during tensile part of the cycle at low temperature. And the repetition of this process leads to crack initiation and further growth of the crack. In order to investigate the crack propagation, longitudinal cuts were prepared from the tested specimen and investigated using electron scatter diffraction technique. And the image on the left side confirms that crack path follows the grain boundaries in in-phase type of loading, while in out-of-phase type of loading, transgranular crack propagation is typical. Now let's have a look at the effect of the loading conditions on fatigue life. And from the figure we can see that cyclic straining at 700 centigrades is less damaging than in-phase type of loading, but more damaging than out-of-phase type of loading. However, for small saturated plastic strain amplitudes, this isothermal straining and out-of-phase cycle leads to identical fatigue lives, while for large plastic strain amplitudes, the fatigue lives in isothermal straining approach the fatigue lives in in-phase type of loading. Well, that brings us to the end of the final section, and now I'll just summarize some main points. The experimental study of Sunnicro 25 under thermomechanical fatigue loading conditions leads to the following conclusions. The effect of environment plays a decisive role in damage evolution under thermomechanical loading conditions. And intensive oxidation of grain boundaries during in-phase leads to early cracking of the grain boundaries and propagation of the cracks into volume of the material in intergranular manner. And similar mechanism was also found for isothermal straining at 700 centigrades. And in outer phase, cycling homogeneous oxide layer is formed while the specimen is in compression. And delayed cracking of the oxide leads to development of cracks perpendicular to loaded axis. And this localized repeated oxidation and cracking of the oxide results in transgranular crack growth. And the knowledge of the relevant damage mechanism allows understanding differences in fatigue life in outer phase and in phase type of loading. Thank you very much for your attention.